Good afternoon, everyone. My name is Shivam. I am going to present NLtoPDDL, which is essentially a domain authoring tool that acquires planning domain definition language models from natural language instructions. I performed this research at Delft University of Technology in collaboration with Dr. Neil Yorke-Smith. Predominantly, there are three ways to acquire domain models: manually, automated using structured data, automated using unstructured data. In manual domain model acquisition, subject matter experts collaborate with knowledge engineers to encode domain knowledge in PDDL. This is a time consuming and an error prone effort. To tackle this limitation of manual encoding, automated domain learners generate models from structured data such as plans or plan traces. However, these inductive algorithms require large amount of plans, and thus there exists a causality dilemma, as it is hard to get data without the domain model itself. Learning domain models from unstructured data, such as natural language instructions, is a recent paradigm. Subject matter experts innately think about the domain in terms of a natural language, and the data itself is also readily available. Our research focuses on this paradigm. Automated domain learners can be classified based on the environment they work in or based on the learning technique they used. NLtoPDDL, like Locum family of algorithms, works in a deterministic actions and no state observability environment. In terms of learning technique, NLtoPDDL uses elements of transfer learning, deep reinforcement learning, human in the loop, and analytical learning. If more data is provided, it is also capable of doing inductive learning. Two NL research papers form the basis of this research. Let's have a look at them. In 2017, Framer solved the problem at hand in two steps. First, extracting action sequences from natural language instructions, and then using these extracted sequences to learn a domain model using locum-based algorithm. However, it requires the use of restricted natural language formations, which isn't handy in the real world. The other paper, extracting action sequences using deep reinforcement learning, overcame restricted text limitation of the framer and did a better job at action sequence extraction. It employs two dequants, one to extract action names and the other one to extract action arguments. It achieves state-of-the-art results but uses word-to-vec embeddings, which has an issue like not handling out-of-vocabulary words. This limits its generalizability to unknown or cross domains. NLtoPDDL improves upon both approaches. First, it incorporates contextual embeddings like BERT into EASDRL, which boosts its performance and generalizability. Second, by re-implementing the Locum2 algorithm in a Jupyter Notebook environment, it provides an SME with flexibility to visualize and modify each step of the algorithm to acquire better quality domain models with less amount of data. Now let's look at the details of how all this materializes. In phase 1, we train both action and argument, extracting dequants on 3 pre-annotated datasets. Microsoft Windows Help, cooking recipes, and WikiHow Home and Gardening. We encode the words using stack embeddings and then use a convolutional neural net as a Q estimator. The DQNs can perform only two actions, either select or reject a word. A positive reward is given if DQN guesses the action or argument correctly, and vice versa. In phase 2, the trained DQNs extract an action sequence from an unseen process manual. The unseen process manual can be of an unrelated cross-domain. After some ambiguity reduction like lemmatization, the extracted action sequence is passed through interactive locum algorithm, where a user can interact with transition and state diagrams of object types in a domain. You can edit the transition graphs by opening GraphML files in Cytoscape GUI or via widget in the notebook itself. You can, for example, modify the nodes, edges, and change weights. In the end, a PDDL model is generated from the state parameterized finite state machines, which are learned behaviors of each object type. Let's look at how action sequence extraction went. There is 5 to 7% improvement in F1 scores in just one epoch for contextual approaches. You can see the generalizability of contextual approaches as their performance does not drop for the unseen test set. It does so for static approaches. Qualitatively, we can see contextual ESDRL does not miss out on out-of-vocabulary words and also performs better in terms of identifying exclusive OR actions, thus avoiding safety-critical flaws like this. Coming to the results of domain model acquisition, iLocum was able to determine correct behavior about the objects of the domain. Without human in the loop, it only one-shots shallow models, but they are easy to modify. For instance, in a related domain transfer learning, it was able to recognize two types of sandwiches, gluten-free and gluten, and created two actions for making them, make one and make. For a non-strips domain, we can leverage research in NLP by performing named entity recognition on time. A good quality PDDL model of durative T-domain was learned. We are able to learn about a behavior of a spacecraft type of object using the weights of DQNs trained on home and gardening and cooking datasets. This cross-domain transfer learning in domain acquisition is a consequence of NLP transfer learning employed in phase 1. You can try all this yourself. You can put your own instructions, extract action sequences, interact and edit transactions, state machines, and incrementally build a quality PDDL model all in just one Jupyter notebook. This is available at GitHub repository. In conclusion, NLtoPDDL is able to learn shallow models which could be used in model light planning or can be enhanced by subject matter experts in an interactive environment. The models can leverage the research in NLP to learn complex behaviors and states. Since the framework has decoupled components, it is easy to plug and play. Some suggestions for the future include using scalable asynchronous methods or theoretically sound alternatives to DQNs, training on multiple words to account for adjectives and compound nouns which often form action arguments. Finally, a user study of SME's interaction to help validate the effectiveness of iLocum. This concludes our talk. Do you have any questions?